Hey, Math 3. Hope you're not missing me too much. Today's Thursday. You should be watching this. And this is now starting week 18. We are in the home stretch. Ignore that, sorry. Today you are watching 10.5, this ed puzzle, and you will get credit for this for your work today. Tomorrow you are just going to have a work day in class on 10.5 in Big Ideas, and it'll be due at midnight on Sunday. Then I will be back on Monday with my new name. And so we'll spend that Monday just kind of recapping, going back over everything you've learned virtually, kind of 10.3, 4, and 5 to make sure we're on the same page. We might introduce a little 10.6 on Monday, but really we'll do that on Tuesday. And then Wednesday and Thursday of that week, we'll review. So I'll post that review on Wednesday, and then we'll test that following Friday. Okay, so that's kind of our week in a snapshot. So you just have the ed puzzle today, and then Big Ideas due Sunday night. All right, so let's dive in. I want to make sure that we are remembering things that we learned at the beginning of this unit. So take a minute and see if you remember how to calculate the mean and the standard deviation of these two data sets. So use your calculator, plug it in, we'll check our answers and get going. Okay, so hopefully you paused your video. Let's see if you got it right. So this is what I got, a mean of 185.8 for the monthly cell phone bill, and with a standard deviation of 43.4. Number 2, a mean of 4.8 and a standard deviation of 3.6. Drop me a note in the ed puzzle if you have a question about that. Okay, so this next section, 10.5. 10.5 is all about making inferences from sample surveys. So basically our goal is to answer the question, how can you use a sample survey to infer a conclusion about a population? So a few things going on in there. We've talked about sample, we've talked about survey, we've talked about population, but this word infer might be new. And so basically to infer something or make an inference is just to conclude something backed by evidence. So you have reached a conclusion by some kind of evidence, right? So it's not just a guess. It's not, picking an answer out of thin air. It's backed by evidence. All right, so let's dive in a little bit. Let's investigate. Let's say that you conduct a study to determine what % of the high school students in your city would prefer an upgraded model to their current cell phone. I think we all would, right? Based on your intuition and talking with a few acquaintances, you think that 50% of high school students would prefer an upgrade. You survey 50 randomly chosen high school students and find that 20 of them prefer an upgraded model. Based on this sample survey, what % of the high school students in your city would prefer an upgraded model? Well, this kind of goes back to the very beginning of the unit when we were talking about, okay? We found that 20 preferred the upgraded model, and we're taking that out of the 50 that we chose, right? So 20 out of 50, punch that into your calculator, you're gonna get 0.4. So that turns into 40%. Okay, so 40% of the high school students in that city, in that would prefer an upgraded model. Sorry. Okay, well, in spite of the sample survey, is it possible that 50% of the high school students in your city prefer an upgraded model? Absolutely, right? If we have 50,000 high school students, we only sampled 50 of them, and 20 of the 50 preferred it. But it is still possible if I have more data sets and I ask more and more students. 40 is pretty close to 50. So it's pretty possible that 50% of the high school students would prefer that if I surveyed more students. Okay. Well, to investigate the likelihood that you could have selected a sample of 50 from a population in which 50% of the population does prefer an upgraded model, let's say we create a binomial distribution like the one below. From this distribution, we want to estimate the probability that exactly 20 students surveyed prefer an upgraded model. Is that likely to occur? Let's see. First thing I want to point out is this word binomial distribution. We've been using the word normal distribution mostly. Binomial, it's very similar. You're like, Miss L, it's the exact same shape, right? The only difference is normal is more generalized. It's continuous. It's if we have a ton of data points. Binomial is a little bit more defined. We have a set number of data points. Okay. So we estimate the probability that exactly 20 of the 50 prefer an upgraded model, right? And we want to see if this is likely to occur. Well, if you look at where this happens, it's just above the 0.04. I'm going to say it's at 0.042. So my probability, I love when the pencil works, right? When my probability is at about 0.042, if I read that graph correctly. That's a very small probability, right? If you look up 0.1, that's a higher probability. These up here, there's a likelihood that that's true, but 0.042, that's too small. So I'm going to say, nope. Just practicing looking at the graph. All right. But can we estimate a population mean? Now we've been using mean a lot, that word, right? But we have been using sample mean, not population mean. They're very connected. They're basically the exact same thing. One is just going to be a little bit rounded. We're modeling the situation with a sample mean of the population mean. Okay, so it says the number of friends for a random sample of 40 teen users of a social network website are shown in the table. We want to estimate the population mean. I want you to take a second, use your calculator and find the sample mean, what we've been doing, meaning find X bar. So pause your video and find X bar. Okay, hopefully you found X bar to be 299.15. Okay. All we have to do for estimating the population mean is we're going to round. 299. Done. Okay. So if you need to jot yourself a note, typically we use that mu for the population mean, and we're going to use this for the sample mean. At the beginning, we used these a little bit more interchangeably, and now we can define them a little bit more. Okay, so go ahead and test that out once more. Now with this set, we have another random sample of 30 teen users, and we want to estimate the population mean based on our sample. So we're using our sample to estimate the population mean. Take a second, see if you got it. Okay, so let's see. Hopefully you got 294. So again, by just plugging this into your calculator, like we did at the beginning of the unit, finding X bar, and then just rounding it to estimate the population mean. Okay, can we estimate population proportions? Okay, let's kind of talk about what that means. A student newspaper wants to predict the winner of a city's mayoral election. We've got 2 candidates running for office, A and B, and 8 staff members conduct surveys of randomly selected residents. The residents are asked whether they will vote for candidate A. Here are their results. Okay. First question asks, based on the results of the first 2 sample surveys, do you think that candidate A will win the election? Let's back up a second. To win an election, if there are 2 candidates, I need more than 50% of the votes, right? Because if there's 2 candidates, that's it, right? Even if I have 51% of the votes, I'm gonna win. If I have 48, I'm gonna lose. Okay, so let's look at these first 2 sample surveys. So I'm just looking at these 2. And this chart shows the sample size, so maybe how many we asked or were polled. Out of the 5, 2 said they were going to vote for candidate A, which turns into 40%. Then we surveyed a few more, so now we have a sample size of 12. 4 of them said yes, so that's 33.3%. Based solely on those 2 sample surveys, candidate A is not winning, right? We're below 50%. So no, because less than 50%, right? And I need 50% of the votes to win. But check out what happens. Let's look at the entire table. Now, do we think that candidate A is going to win the election? If I look down here and increase my sample size to 200, it's going to increase the validity of my results. And out of 200, 118 are voting for candidate A, resulting in 59%. It's greater than 50%. Yep, candidate A is winning. So the point of this is to really show that as we increase our sample size, we get better results. Okay, so what do you think? Let's bring it back to kind of the classroom. Let's say we have two candidates running for class president, and this table shows the results of 4 surveys of random students in the class. The students were asked if they would vote for the incumbent. Now, note that the incumbent, if you haven't heard that word before, it just means that the person that's currently holding office. So in this case, it's the person that's currently the student president. So do we think that that person is going to be reelected based on these results? Take a second, think about it, drop your answer in the Edpuzzle. Okay, let's check our answers, see what you got. No. So based on these results, no. As the sample size increases, the percent reaches only 42.5%. So that's not enough to win, right? If we look at that percent. Okay. All right. Well, let's say that a national polling company claims that 34% of US adults say math is the most valuable school subject in their lives. So you survey a random sample of 50 adults. Now in section 10.2, we discussed a little bit about how you can run a simulation to model situations. So we're going to do that. And we're going to use our calculator actually to do this one for us, not a software program. So let's simulate 80 random samples. Each of those samples is 50. We're going to use our calculator. I'll walk us through in a second. So we want to generate 50 random numbers from 0 to 99 for each sample. Okay. We're going to define 1 to 34 to be those adults that say math. Okay. So in your calculator, if you go to math, which is this button here, and you toggle over to probability, it says PRB, and you go down to random integer. We've done this once before, but just going over it again. And you plug in 0, 99, 50. So that's your generating the numbers from 0 to 90 50 times. Okay. So I'm going to find that set of numbers, and you'll have a string of numbers then in your calculator. For example, mine says 33, 99, 20, 79. It'll go on for 50 sets, right? Well, now I've already done this for us. Well, the book did, but let's say we put this now on a dot plot, right? And we turned our set of numbers into more frequency. Okay, so here's our random sample, 15 out of 50 and 25 out of 50. We want to know, what can you conclude about the accuracy of the claim that the population proportion is 0.34 when 15 adults in your survey say math is the most valuable subject? Well, if we're saying 15 of the 50, that would correlate to 0.3. Right, if you punch that into your calculator. But in our simulation, if you look at 0.3, there's 1, 2, 3, 4, 5, 6, 7 of the entire 80 samples. The percentages there about match, so the claim is probably accurate. Okay, fair. What about the claim? And remember, we talked earlier about a claim is kind of like a hypothesis. What can you conclude about the accuracy of the claim when 25 adults in your survey say math is the most valuable subject? Well, 25 out of 50 equals 0.5. If you look up at 0.5, I only have 1 dot, right? That's it. Only 1 of the 80, it's pretty low. Very unlikely that this would occur, so the claim is probably not accurate, probably not true. We'll assume that the true population proportion is 0.34. We want to estimate the variation among sample proportions using sample sizes, using samples of size 50. Well, if we look up here, it's pretty normal distributed, right? It's a bell curve. So 95% will fall within 2 standard deviations of 0.34. That goes back to your chart that we worked on at the beginning of the unit. 95% of our data, that's that 68, 95, 99.7 rule within 2 standard deviations. So 95% of the time, a sample proportion should lie in that interval. Okay, all right. If you have a question about any of that, drop it in the Edpuzzle now. Okay, just a few more things to go through here, and it's margin of error. When a random sample of size n is taken from a large population, we do have to consider our margin of error, okay? And basically the margin of error is just plus or minus 1 over the square root of the sample size, okay? This means that if the percent of the sample responding a certain way is p, okay, so we're going to call it that, then the percent of the population who would respond the same way is likely to be in between an interval where we subtract it and then we add it to the margin of error. All right, let's see what this looks like. And actually, I'll have you pause your video, write down the formula for margin of error. Don't stress too much about this. It'll come out as we kind of practice and do examples, but write down the formula for margin of error. Okay, let's do an example. So in a survey of 2,048 people in the US, 58% said that television is their main source of news. We want to know what the margin of error for that survey is. Well, the formula we just discussed says, I'm just going to use M. If you look back, right, margin of error plus or minus 1 over the square root of n. N is our sample size here. So I'm just going to plug this in, plus or minus 1 over the square root of 2,048. I don't know what that is. 1 over the square root of 2,048. And we get plus or minus 0.0221. Okay. All right. Now we can leave it like that. Typically in margin of errors though, I'm just gonna move that, sorry. Typically we turn that into a percent. So I'm gonna move this to points, so 2.21%. Okay. Well, now we wanna know the interval that it's likely to contain the exact percent of all people who use television as their main source of news. Okay. Well, before it said, we just have to add and subtract on either side. Our margin of error is going to be on either side of this 55% of what they said, because there could be some error. So I just take my 55 and I have to plus or minus 2.21. So on the lower end, if I subtract 2.21, so 55 minus 2.21, I get 52.79%. I'm going to add it, and that's 57.21%. There's my interval by adding and subtracting that margin of error. Okay? All right, last skill to test out for me. Take a second, show me what you've learned. In a survey of 1,028 people in the US, 87% reported using the internet. Give an interval that is likely to contain the exact percent of all people in the US who use the internet. Ready, go. Okay, let's check your answers, see how you did. Between 83.9% and 90.1%. So again, to walk you through this, we first had to find our margin of error by plugging into the formula and then adding and subtracting it to either side of the 87%. Okay, all right. So what I'd like you to do now is jot me a note. How do you calculate margin of error and why does it decrease when the sample size increases? So pause your video and answer that. Okay, and I'll read those later. But congratulations, you are done with video lessons. I know it has not been super fun and probably pretty boring in class, and I apologize for that, but I will be back on Monday. I want you now to work on 10.5 and big ideas. It's due Sunday night at midnight. And tomorrow is going to be completely a work day on big ideas. So you can go ahead and get started, or you can wait until tomorrow in class and start, and then finish it up for Sunday night at midnight. You might be able to get this one done in class, most likely. So I will be back on Monday, and I look forward to catching up. Okay. Last thing, if you have any questions about today's lesson, drop it in that puzzle. Bye, y'all.